Hello, Internet. It looks like I have a floating blob over my desk. Let's poke it and see what happens. Ooh. You can see that it reacts to my hand when I draw my finger close to it. This is inspired by things like ferrofluid, magnetic slime. Just wanted to see if I could get a similar effect on the Hololens. And you can see it's kind of like a magnetic slime in that as my finger gets closer and closer and closer, it'll eventually get drawn to it, and I can even poke in to the surface. So you can see that I'm actually distorting the surface of the sphere with my finger. So I can run my finger across this blob and it will distort accordingly. So if I poke into it, if I pull away from it, I can even use two hands and manipulate the blob from two different directions. So you can see that I'm using one hand in one direction and the other hand in another direction, just to kind of see what would happen. And it's not perfect, but I do like where I am with the effect. And I'm not using one finger due to a technical limitation. It's more so that at this scale, at this tiny little desktop scale, it's kind of hard to get something that looks good operating on all the fingers. It just was hard to tell what's going on. So this is the best compromise I could make. And it's very responsive. It may not come across in the video, but it actually responds very well to my hands running across the view. And you can see that I can distort it from any angle. And I'd like to get into a little bit about how this was done, a little bit about the journey that I took to get here, the different options I explored. And in general, this was an interesting project, and I'm glad that it's running well on the Hololens. So let's fire up Unreal and see what happens as soon as I had my fill of poking the blob. It's a very nice, it's very zen to play with this blob. Alright, moving on. Let's take a look at the first attempt I made towards this effect. You can see a very similar blob and the simulator hands provided by the Mixed Reality Toolkit. This blob tracks 3 points on each hand, the index finger, the pinky, and the thumb. And this effect looks fairly fluid and organic. However, it was not practical to run on the HoloLens. This is a ray marching based effect, which is very similar to how some people might do meta balls. And while it runs well in the simulator, it runs well in VR preview, it does not run well standalone on the actual device. It's just too heavy on the pixel shader. Despite that, I would like to examine what went into this effect, as there are a few good takeaways. The effect is constrained to this disc that gets billboarded against the camera on every tick, and you can see that it acts as a viewport into this ray-marched scene. So what happens is for every pixel of this disc, we're actually going to render a pixel of that ray-marched scene. And you can see that the background is not clipped away because pure black will just be clipped to transparent on the HoloLens anyway. I would just like to touch on some of the key concepts of this particular material. If you would like to see details, please feel free to visit the GitHub link in the video description. We established some material parameters to bring in the predicted finger positions for each hand. We then passed them to a series of custom nodes. Custom nodes are a way to bring your own HLSL code into Unreal Engine. For better or worse, Unreal Engine will preserve your code exactly as it outputs it to the final shader. The basic idea behind ray marching is to travel along the camera's view vector until we get close enough to a surface. And we can do this pretty intuitively with a while loop, which makes this a great candidate for a custom node. Without digging into the code, I just want to touch on some of the concepts of custom nodes that will carry us even into the example that we've seen running on the HoloLens. For one, you can set variable numbers of inputs and outputs. You can see I have different inputs here to represent the parameters that my function is accepting, and I can define additional outputs that I can feed into other nodes in my material, which makes this behave a little more like other nodes or material functions. You can also see that I've chained a few of these custom nodes into each other. And that forces Unreal Engine to compile them in a specific order, which is going to also benefit us in the next example. To see what that might look like, let's get a look at the shader code that's actually output for this material. I can copy this into a text editor, and what Unreal is going to do is wrap all your code inside a function called custom expression. So you can see that custom expression 0 might be the first custom node that has to be compiled. Custom expression 1 would be the next, and so on. So in custom expression 2, you can see that I'm able to actually call the code within other custom nodes by referring to them as custom expression 0, 1, 2, 3, and so on. You can also see this in-out function for my normal representing that output pin that we see in the material editor. The only odd thing about these custom nodes is the type of each parameter is not fixed. If you look at the inputs definition, you'll see I only give them names. It will infer the type based on what you're actually feeding it at the time within the material editor. So you can see that I've essentially fed them complete zeros in the type that I've expected. So if I've expected a float 3, a float 4, a single float, as long as the types match, I can call it in the way that I expect within the function which depends on them. So that's another trick to consider if you want to chain these custom nodes together. The example running on the HoloLens is actually a sphere cut in half, which always billboards against the camera, since we can only see half the sphere at any time anyway. The event graph is actually fairly simple. On event begin play, we'll want to associate that dynamic material instance so that we can update the material parameters with the finger positions. Then on every tick, we're going to billboard against the camera position, and we're going to pull the positions for each hand. We can do that with the get motion controller data block, which will take either a left or right hand, and that outputs an XR motion controller data structure. What we should do is then first check if it's valid, check if it's an actual hand, and I also like to ensure that the length of the hand key positions array has some content in it. If all of that is true, then I can start to update the material parameter. And in this case, I'm using node 1 for the index finger on the right hand and node 2 for the index finger on the left hand. And it's fairly straightforward to get the position of a particular joint on the hand, as the hand key positions and hand key rotations are actually synchronized. And you can use the E-hand key point, enum, to pick pretty much any joint in the hand with great accuracy. Even if the finger is slightly obscured by other fingers, the HoloLens still does a great job at predicting where those exist in 3D space, and it's fairly responsive. Once we have that position, I feed it into a linear color that I can pass into this vector parameter. This nodule tip radius is actually just set to 1. And the reason I do that is because if I don't see the hand, I'm going to pass all zeros to the parameter. So in this way, it's either 0 if it's invisible or off screen or not predicted correctly in some way, and if I have a valid prediction, it will be 1. So this will let me easily cancel out the influence from a hand that's not actually on screen. The previous attempt is far too pixel shader heavy to work well in the HoloLens, so we need a solution that does most of the work within the Vertex shader, displacing existing geometry. I tried a few different techniques to achieve this goal, and it seems that the simpler solution actually worked out fairly well. Here's a simple implementation where we can get vector Pn, get its magnitude via the length function, and then return the same Pn times 1 over k times that magnitude squared. There is one optimization we can make here. This length function essentially does a square root, and all we're doing with it is squaring it back anyway. So instead of getting the distance, we can get the distance squared by dotting Pn against itself. And that will be sufficient here. So this is essentially all the HLSL logic we'll need to displace positions on the sphere towards a specific node. The actual code in the example is very much the same, except I'm changing k depending on how much I'm actually poking into the sphere. I'm not sure if this is really physically accurate, but I wanted the effect to be more pronounced if I'm poking into the sphere versus pulling out. So it would have the effect of poking into a soft pillow or marshmallow. That takes care of a single node, but what about this rippling effect and the other node? The ripples are simple enough. Using a panner node, we can pan the UV coordinates against time, and of course, take in the fractional part to avoid any precision errors. This becomes more important on mobile devices especially, as sometimes you'll see the texture panning stutter even though the frame rate is overall very good. We feed that panner node into a texture sample, which is just using one of the noise textures included in the engine itself. We can then take the magnitude of that and multiply it by the vertex's normal to displace it along the surface. We then feed that displacement into the displacement custom node here as well. Then we add everything in such a way so that vertices which are displaced more by each node are going to be displaced less by the ripple here at the bump offset. Next, let's take a look at the pixel shader, which actually determines the color for this surface. And we can see that this is an unlit material, which means we have to approximate the lighting ourselves. The first step is going to be gathering the normal for that pixel. If we take the absolute world position of that pixel, we can compare it to the world position of neighboring pixels using the ddx and ddy functions. This will approximate the partial derivative of the world position across the x and y axis, which essentially gives us a coordinate plane across the surface of a single triangle. Taking the cross product of that will give us the normal for that entire triangle. So you can see if I set the preview to a sphere rather than my highly tessellated hemisphere, you can see that it has this flat shaded look because the normal is going to be consistent across an entire triangle, for better or worse. Another approach could have been to recompute the normal within the vertex shader and then interpolate that across to the pixel shader for a more smooth shaded approach. I'm going to go back to my preview mesh, which is a very high polygon hemisphere, or higher polygon, at least in this sphere. You can see that it has almost 41,000 triangles in just the one half of the sphere that's represented, to give it a nice, smooth, gooey surface. The rest is straightforward. Once we have this normal, we can use it to look up into a cube map here, and we can also use it to interpolate between two colors to give the illusion of lighting. And that's it. That's the pixel shader. And that's the material. And here is what that looks like within the editor's viewport. And you can see the simulated hand behaves very similarly to the hands that we actually predicted on the HoloLens. And this is a very good tool to iterate quickly on things. It's much easier to iterate on simple effects using the simulated hands, which can actually support things like clicking and grabbing. So you can see that as I move the index finger around, it's fairly representative of what I would see on the actual device, versus actually having to deploy to the device each time. Unreal also supports this VR preview feature, which will essentially render the effect on your computer and then stream the output to the HoloLens device. So you can still preview a sense of how it would look and feel, but it would still be rendered on the computer itself. And that's all, folks. Thank you so much for watching. Hope you have a wonderful day.